Hello, my name is Pedro Machado and I'm here to present the work on strawberry detection using a heterogeneous multiprocessor platform at the ARIS 2020 workshop on perception, planning and mobility in forestry robotics. I'm part of the Computational Neuroscience and Cognitive Robotics group at Nottingham Trent University, and our team is composed by Samuel Brandenburg, myself, Nikesh, Lama, and Professor Martin McGinnity. So today I'm going to talk about the research aims, fruit grasping, YOLO version 3, edge computing, results, discussion and future work, and acknowledgement. In terms of research aims, our objective is to detect strawberries at the edge using deep learning algorithm. And in terms of aims, is to create a custom YOLO version 3 algorithm and accelerate the custom YOLO version 3 model using a Xilinx DPU fitted for the ZCU 104 Zinc Scale evaluation board. Before going into details on how the work was done targeting the Xilinx board, I'd like to talk a bit about the fruit grasping. And in terms of the fruit grasping, we defined that there are 5 steps. The first step is the fruit classification. Use the CNN algorithm to classify fruits in the image. This is the part that we'll be looking in this project. Pose estimation, estimate the best pose to pick the object using a robotic arm similar to the one in the figure. Path searching, search the best path assuming the current position of the object in the scene. Path planning, predict the trajectories of moving objects and estimate the optimal path while avoiding collision with these objects. And finally, grasping the target fruit. And for this we are using a robotic platform which is composed by the Dennis GMV robotic platform fitted with the Intel EOS ST435 and a Xilinx Zinc Ultrascan Plus family. So we have the fruit classification, which is the most computational intensive algorithm running on the Field-Programmable Gate Array, and the other 4 steps will be running on the processor system. In this case is the ARM Cortex quad-core A53. So for doing this work, we selected the YOLO v3, which is a CNN algorithm, a very efficient CNN algorithm composed of 53 convolutional layers and the fully connected layer. This work was presented by Redman and Farhadi, and I'm leaving here the link for those of you who want to know more about the YOLO v3. The reason again why we use the YOLO v3 is first because it's supported by the Xilinx VTZI tools, and second because this is a very efficient algorithm, as you can see on the work presented by Redman and Fardi. So let's talk about edge computing. For performing edge computing, we need a multiprocessor system. This is basically a Xilinx Ultrascale Plus, which on the same chip here, we have a very powerful ARM A53 processor to allow us to run an operating system. It also includes a GPU for accelerating the graphical elements, and the Field-Programmable Gate Array to allow us to describe the neural to accelerate the neural network, and it also has a real-time unit, which is ARM Cortex M5, but we are not going to use it, so I'm not going to focus on this. For this work, we focus on the processor system and on the field-programmable array. So the initial steps is to train ULV3 on darknet using a regular workstation with a GPU, and using the darknet framework provided by Redmond. Adapt the ULV3 to run on the ZCU104 using the Xilinx DPU IP, and for this we use the Xilinx VTZI tools. Quantize the model. Here we can see that we have a network using, for example, floating point 32 bits, and the II quantizer, what does is to convert those into those weights into integers of 8 bits, and with this allow us to save resources on the field-programmable gate array, and of course run the custom ULV3. So the first step is to design the DPU using the Xilinx Vivado. The second step is to parameterize the DPU to ensure that we are taking advantage of the space that we have available on the FPGA, and to allow us to optimize the algorithm to run on the FPGA. And the third stage is to compile, and here we can see the report that was generated, where we can see the resources usage on the field-programmable gate array. Here we can see that we are using around 50% of the resources, meaning that there's still some space to perform some more optimization. And of course, then to run ULV3 on the FPGA. So at the end, we were able to detect 30.05 frames per second, which is a relevant improvement. So we ran the same on the processor system, which is equivalent to a Raspberry Pi 3 Model B, and we got 2.66 frames per second. We are talking about the ARM A53. Furthermore, we managed to get an accuracy of 78.3% using the validation set of 146 image. The accuracy is still around 78.3 to 80%, which means that more work can be done, and we'll be exploring and improving the neural network, also to look at the annotations, trying to improve the accuracy, while again looking at the DPU on the FPGA side to try to increase the number of DPU cores, and with that we expect to get better performance in terms of frames per second. We have a short video to show you where we can see the classification. Again, it's possible to see that there is still a lot of work that can be done, for example, in terms of occlusion, and also because we believe that using the depth we'll be able to improve the classification and get more true positives. So, in terms of discussion, the main contribution of these papers are strawberries detection at the edge using deep learning algorithm. We managed to accomplish this goal. The proposed algorithm enables the strawberries detection at the edge at 35 frames per second and exhibiting an accuracy of 78.3%. In terms of the future work, we'll utilize the VT's AI optimizer for achieving a higher frame rate. The VT's AI optimizer allows us to do, for example, pruning, which allows us to reduce the size of the network. And again, this will be one of the reasons why the neural network will tend to work faster. Use the depth and color for improving the classification. It's known that the CNNs tend to be very biased on the color. So, for example, in situations where, for example, imagine that you have crops, mixed crops with tomatoes and strawberries, you're probably going to get too many false positives. So, we intend to use the depth information to improve the classification and implement the other 4 steps for grasping the strawberries, which is pose estimation, path searching, path planning, and grasping. We would like to thank Sundance, Sundance multiprocessor, for facilitating access to the Xilinx training, and this was a very important step. Without the Xilinx training, it would not be possible to get this project going. And landing the GMV Dennis robot that you can see here, the Xilinx VCU104 board, and the Sundance VCS1 board. And the VCS1 board is the system that we are targeting to use on the GMV Dennis robot. And the reason for that is because the VCS1 is an industrial grade and is a PCI 104 stackable board, which is basically designed for the type of application that we like to explore. Also, because allow us to connect directly up to 4 USB Type-C cameras. Thank you very much for watching this presentation, and if you have questions, I'm happy to answer your question, or please just send us an email and we are happy to answer the email and answer all those questions. Thank you.